In econometrics, we are interested in estimating relationships between economic variables. So we might have a dependent variable y and an explanatory variable x. And in order to construct our estimators, we minimize the sum of squares of the estimated residuals. So we're going to minimize the sum of the ui hat squareds by differentiating with relation to whatever we are choosing. So we might be differentiating with relation to the beta naught hat, the intercept that we choose, or we might differentiate with relation to beta 1 hat, the slope parameter that we choose. So we can also estimate OLS by imposing certain constraints. So let's impose that the intercept, we're going to impose that the relationship that we're going to estimate is that beta naught is equal to 4. So the relationship that we're going to estimate is yi is equal to 4 plus beta 1 hat xi plus ui hat, and we want to try and construct the optimal estimator by minimizing the sum of squares of these residuals. So the first thing to do would be to write down the residuals. So we can write down that the ui hat is going to be equal to yi minus 4 minus beta 1 hat xi. All that we've done there is we've rearranged our initial specification, and we can then write down the sum of squares of these ui hats by saying this is the sum from I is equal to 1 to n of ui hat squared, which is equal to the sum from I is equal to 1 to n of yi minus 4 minus beta 1 hat xi, all squared. Now we're going to want to differentiate this expression with relation to what we're choosing, which is beta 1 hat. So we're going to differentiate the sum from I is equal to 1 to n of ui hat squared with relation to beta 1 hat, which is equal to the derivative with relation to beta 1 hat of the sum from I is equal to 1 to n of yi minus 4 minus beta 1 hat xi, all squared. Now in order to differentiate this is effectively a function of a function, so we're going to take the 2 down the front, we're going to lower the power by 1, then we're going to differentiate what's on the inside with relation to beta 1 hat and multiply everything by that derivative with relation to beta 1 hat. So this is going to be equal to, we take the 2 down the front, so this is going to be 2 times by the sum from I is equal to 1 to n of yi minus 4 minus beta 1 hat xi. We then multiply all of this by the derivative of what's inside the brackets. Differentiating y with relation to beta 1 hat is 0, differentiating 4 with relation to beta 1 hat is 0, but differentiating minus beta 1 hat xi with relation to beta 1 hat is just minus xi. So that's going to be multiplied by xi, and then it's a minus sign. Then in order to find the optimal beta 1 hat, we set that equal to 0. So let's indicate that we've chosen our beta 1 hat by putting a beta 1 hat star. So we can now rearrange this a little bit to give us that this means that, let's get rid of the minus 2 because we can divide left and right by minus 2. We've got the sum of yi minus 4 times by xi. We've also got the minus beta 1 hat times by the sum of the xi squareds. So let's rewrite that as the sum from I is equal to 1 to n of yi minus 4 times by xi minus beta 1 hat star times by the sum of the x squareds is going to be equal to 0. So then we can rewrite this again. We're going to move the beta 1 hat, sum of the x squareds, over to the right hand side. So we can write that the sum of the yi minus 4 xi is equal to beta 1 hat star times by the sum of the x squareds. So we can now just rearrange this to give us that beta 1 hat is equal to the sum from I is equal to 1 to n of yi minus 4 times by xi over the sum from j is equal to 1 to n of xj squared. So now, having imposed our constraint that the intercept needs to be equal to 4, we've managed to construct our estimator, which is the sum of the yi minus 4xi over the sum of the x squared. Now, there is an easier way that we could have done this. In order to see the easier way, let's remember what we did when we estimated the relationship where we specified that the intercept was equal to 0. So if we estimated yi is equal to beta xi plus ui, the optimal estimator, beta star, was equal to the sum from I is equal to 1 to n of yi xi over the sum of the x squared. We could have just written in this example the relationship that we're estimating is yi is equal to 4 plus beta 1 xi plus ui, which means that our dependent variable we could convert to being yi minus 4. We could take the 4 over to the left-hand side and just give us that the relationship that we're estimating is yi minus 4 is equal to beta 1 xi plus ui. But then our dependent variable is yi minus 4. We're estimating a relationship without an intercept, so we've just got this xi as the explanatory variable. So we could have substituted that into beta star to give, instead of yi here, having that yi minus 4, and we would have got to that same estimator. Now, we can also impose restrictions on the slope parameter. So suppose we wanted to impose that beta 1 is equal to 2. Effectively, the model that we're estimating is yi is equal to beta naught plus 2xi plus ui, and we're going to try and minimize the sum of squares of the fitted residuals. So the sum of the ui hat squared is going to be equal to the sum from I is equal to 1 to n of yi minus beta naught hat minus 2xi all squared. And the only thing that we're choosing here is beta naught hat, so we're going to differentiate with relation to beta naught hat. We do exactly the same thing as we did before. We take the 2 down the front, we lower the power by 1, and then we multiply by the derivative of what's inside the brackets with relation to beta naught hat. So this is going to be equal to 2 times by the sum from I is equal to 1 to n of yi minus beta naught hat minus 2xi. The derivative of yi with relation to beta naught hat is just 0. The derivative of minus beta naught hat with relation to beta naught hat is minus 1. So that turns this negative. And the derivative of 2xi with relation to beta naught hat is 0. So we can now set this equal to 0 and say that the optimal beta naught hat is this. Again, we can divide left and right by minus 2 to give us that the sum from I is equal to 1 to n of yi minus n lots of beta naught hat star, because beta naught hat is just a constant, minus 2 times by the sum of xi is equal to 0. And then if we move this over to the right hand side and divide through by n, that gives us that 1 over n times by the sum from I is equal to 1 to n of yi minus 2 over n times by the sum from I is equal to 1 to n of xi is equal to beta naught hat star, or the sample mean of y minus 2 times by the sample mean of x is equal to our estimator. And again, this looks very similar to the estimator that we had for OLS in general for the intercept, because remember the OLS estimator for the intercept, beta naught hat, when we don't specify anything about the slope, is just y bar minus beta 1 hat x bar. And all we've done here is we've replaced the beta 1 hat by beta 1 is equal to 2.